This afternoon, I'd like to introduce Tyler Leeds, who's going to be presenting the Internet X-ray Diagnosing ECMP Failures. It's his first time presenting at NANOG and comes to us from St. John's, Newfoundland. So welcome, Tyler.
You can all hear me. Hi, guys. My name is Tyler Leeds, and I'm a network engineer in the Network Operations Division team at Automattic. Now, I wouldn't be surprised if a lot of you guys haven't heard of us. You've almost certainly heard of a number of our products. We're the company behind WordPress.com, WordPress VIP, WooCommerce, Jetpack, and Tumblr. Probably heard of Tumblr. We're an open source first company. Now, I'm not trying to sell you anything, but this is actually pertinent to what we're going to discuss. We host somewhere on the order of 760 million websites, blogs, e-commerce sites, and podcasts. We enable our customers and our content creators in nearly every country in the world. We provide the platform through our WordPress VIP division for a huge array of everyday websites that you guys probably visit all the time. To that end, several years ago, we began building our own CDN, or content delivery network. And today we maintain 28 data centers across 6 continents. It's some of the cool things we've built to aid in running those data centers and running that network that I'm here to talk to you about. Now, I'll stop for a second and give you guys a warning. We figured that a lot of the folks here, and maybe a lot of the people on YouTube more later, might not be really familiar with how an Anycast CDN operates, or how the intricacies of equal cost multipathing on the internet work. So I'm going to take a couple of minutes and do a quick 101 on both. If you're familiar, then feel free to fiddle with your laptop, and I'll give you a heads up when we get to the good stuff. So the core of a CDN IP is really IPv4 Anycast. And now I suspect most people here have a pretty decent idea of what some of that is and some of the implications it raises. But I figured I'd give this talk to kind of get everybody on the same page from a terminology perspective. Anycast, as we know it, isn't really defined anywhere. It's not really in an RFC or an ISO spec. It's essentially something we as network engineers do to exploit the routing on the internet to accomplish something that's really kind of anathema to the way things are supposed to work. Anycast is essentially the act of announcing the same IP prefix from multiple locations simultaneously around the world. And normally this isn't really what you're supposed to do. Where's the traffic going to go? What happens if routing changes? How can you send traffic back? Essentially, by announcing the same prefix from 28 places, we're depending on the internet through provider IGPs and AS path differences, and sometimes just sort of how geography works, to get our users to the correct data center that is announcing the prefix and that's closest to them geographically. Now, that doesn't always work, and a large part of my day is actually spent sort of managing and massaging the links in the internet to get everybody where they're supposed to be. But generally, it works pretty well okay. And in serving up websites, the duration and the amount of time it takes to do a single request is short enough that when we do reroutes, it doesn't really matter. Now, this does bring up a pretty important point. Now, if users are supposed to get routed to the correct data center, but often aren't, how do you ensure that the content they're actually looking for is where they end up? Most of the data centers in a CDN aren't. That is, they're not major data centers that contain all of our traffic. They are, in fact, just really large web caches. We basically take the largest, most high core count servers we can find. We jam them full of really high-speed storage, and then we pack a rack as dense as possible, and we sort of send them out into the world. But the trick is what happens when you don't hit it. We have a cache hit rate somewhere on the order of 90%. But that extra 10%, as they say, is the rub. That's where we spend a lot of our time. It's important to note that when we do a cache miss, that is, the data that the user asked for doesn't happen to exist at the POP they landed at, we do what's called an origin fetch. So basically, the POP will proxy that connection back to one of our origin data centers. And the origin data centers are essentially the source of truth. They're the place where we house all of WordPress.com and all of Tumblr and all of WordPress VIP. Those are the places where all the databases live and everything is stored. And so that 10%, managing that 10% and that proxy communication is really, really important to us. Automattic is a little bit unusual in that we are both a content provider as well as a content delivery network. And that's a little uncommon. Now, what it means when we do a cache miss, and it's really important, is that when we miss, it's us doing the communication back. And most of the time in my operations role is spent managing those connections back between our POP data center and one of our origin data centers. Because if that connection drops, then it sort of silently causes the user problems. The user won't see that a connection timed out. Everything just gets very, very slow. And because buying like lambdas or waves on international fiber is really expensive, we don't make that connection over any kind of leased lines. We do it all over the open internet across transit links. We typically deploy POPs with between 2 and 5 connections to a handful of local and global NSPs. We try to operate more or less entirely in the default free zone. And what we've noticed while doing this is that a path across the internet that seems loss-free often isn't. And that leads to my next point, which is ECMP, or equal cost multipathing. On its face, it's pretty simple, right? We'd love to provision everything with like 800 gigabit links across, everywhere. But that's not how the internet has been built. It's built, progressively on top of old links are added to new links. And when you do a trace route between 2 points on the internet, it looks like a series of distinct hops, but they're not really distinct. They're actually often the result of many equal cost paths, or often it's layer 3, or maybe there are multiple LSPs. But more likely, they're probably LACP link aggregates. Whatever the reason, the reality is that most of the links are composed, most of those links in between paths are composed of multiple links. Now, while all of those links are sort of supposed to have the same metric, the truth is they're not really all equal cost. For lots of the reasons, the links that comprise an aggregated logical link often have vastly different latencies. And importantly, they also often connect via different router ports that have their own transmit queues and receive queues and buffers. This is kind of problematic. TCP notably really doesn't like out-of-order packets. And more importantly, the ring buffer on your operating system really doesn't like waiting around to reassemble out-of-order datagrams. We probably all remember from sort of basic CCNA, which we all probably got way back in the day, the chapter where they made it really clear that Ethernet is a packet switch network and that they contrasted it with telephony systems, which are circuit switch networks. And it sort of leads to my next point, which is the internet is a flow switch network. In order to keep TCP and the OS ring buffers happy, per packet load balancing is basically never used on the internet. So that's a great statement and all, but like, what does it actually mean? And again, we're still doing the 101 stuff, but we'll basically go back and say, what's a flow? Basically this, generally routers define a flow or a layer 4 flow as consisting of the 5-tuple. And the 5-tuple is the source IP, the source port, the destination IP, the destination port, and the protocol. And for some protocols, really notably ICMP, it's actually only a 3-tuple. That's because there's no concept of a port on ICMP. And why is this important? It's the 5-tuple that the router uses to choose which physical port in some equal cost group, whether an ECMP path or a link aggregate, is used for any given datagram. Essentially, by using ASICs on the hardware, the router will use that 5-tuple to compute a hash and choose a link index. And then it will send it down the link index of the link that was chosen by the routing protocol. It's important to note that the hashing function that routers use is stable, but it isn't stateful. There's not a table you can go in and consult on most routers that will tell you exactly which flow hash gets mapped to which physical port. But it's stable insofar as the ASICs in the router, given a single 5-tuple, that is source port, source IP, destination port, destination IP, and protocol, the router will make the same decision over and over again on every ingressing packet and push it out the same egressing port. And the only thing that tends to vary that those flow topology around and move packets to different ports is when the topology changes. So when you remove a link from a link aggregate, or you add a new path, or a new LSP comes online, those are the sorts of things that will bounce the flow hashes around. And you'd be surprised at how stable the internet actually is. So the problem. We've got through all that. I'll kind of get people back on now. We can, you can look up from your laptops if you've been going through the 101s. Essentially this, we noticed that monitoring the path between 2 data centers with ICMP wasn't working for us. We could run dozens of pings, sometimes hundreds of pings, between monitoring boxes at site A and site Z and come up with 0% loss. Everything looks fine. And at the same time, it would be obvious to the folks running the servers that communication between our POP data center and our origin data center was failing. We'd have timeouts on the origin fetches and those cache fill operations. We use public addressing both on our POP and on our origin. And so each cache fill operation or each origin fetch would generate a new flow. And those new flows would just silently fail because they were traversing an ECMP path. We theorized this, and I think it's pretty clear, is that because ICMP lacks any concept of ports, there's essentially no entropy being generated when monitoring using ICMP. So essentially, your ICMP monitoring flows can't take any advantage of ECMP being conducted through the internet as you go along. Our pings, sort of, no matter how many we would send, would glue themselves to a single permutation of physical links as they went from here to here to here to here. They would pick one permutation and just stick to it. And if that particular link wasn't taking errors, we'd never be able to detect a problem. These problems just sort of silently existed until we would get pinged by our systems team asking us why their proxy connections are timing out. So here's what we did to solve it. This is Pingo. At its core, it's very simple. It generates a series of UDP ping flows between any 2 data centers. By sort of consistently varying the source ports we're sending it from, we're able to trigger a PBR on our egress routers. And the PBR is configured so that certain source ports are always sent using specific NSPs. And that's really important. And on the far side, the same thing occurs. So the response daemon at the other data center does the same thing with the Pong response. It'll send it backwards, and we embed a timestamp in every single flow for each sort of data center and NSP combination we generate. We're using 6 source ports to 6 destination ports per protocol, IPv4 and v6 in production. And so that means we have 36 unique flows for every permutation of source data center, source NSP, destination data center, and destination NSPs. And as you can imagine, this actually adds up across our network to tens of thousands of flows. And by varying the source port and destination port combinations, we're able to generate enough entropy to sort of encourage the NSP's routers to load balance this traffic. And that was really the original goal, was to take advantage of ECMP. Then once we get a response to one of our UDP packets or not, we'll generate several latency percentiles and loss statistics, and then we dump them into a time series database like Prometheus. And then we use that data to essentially generate a few dashboards that give us a lot of insight into what's happening on the inside of our NSP's networks at any moment in time. We're going to go through a bunch of these dashboards, and I know it's a little dry, but I think you'll see some pretty interesting things with how the data is arranged. So we'll go to a sort of a dashboard primer so you can kind of get an idea of what you're actually looking at. First, it's sort of probably a good idea to show you what you're seeing. These are the combined latency and loss graphs for a single combination of outgoing and response providers. So like, I think this one's actually, 3549 outbound with a response that egress from the remote side on 2914. The green line shows the 50th percentile of packets. We actually use median, not mean, so we don't use averages. One of the things we discovered while doing this was that the max ping in any sort of given check is more of a measure of local system latency than it is of the internet. The gray bits, the kind of smoky gray bits, which you can kind of see there behind the green line, those are the 75th and 95th percentiles. Those are important for us because we find that they will start to rise before the 50th percentiles. And it's useful to see links decaying as problems start to occur. The purple dots, or blue in some of these cases, represent the number of lossy flows out of 36. And the yellow bars are the percentage of traffic lost. Got it? And so the actual dashboard is arranged like this. The current path we're using, whatever it might be, is across the top. The graphs below it are all the different NSP combinations, and the rows represent the outbound NSP from the source, or the forward path, and the columns represent the response NSP from the remote side, essentially the return path. Now, it's probably important to note here that we are only showing the worst case scenario path, because that's what we want to see as we're sort of troubleshooting things. There may be, and we'll see them, ECMP paths on these carriers that are just fine. But we're really interested when they're not. So in this example, we're currently experiencing no loss on our current path across the top there. But there's pretty heavy congestion occurring on traffic traversing, so outbound on AS 2914. That's that first, or maybe the second column, destined for this pop. Additionally, it looks like there's also really heavy congestion on the return path towards this pop on 2914 and 7922. And in this case, we have a loss-free solution to the problem where we outbound on 1299 or 3356 and return on 3356 only. and that would be those two middle boxes that look much happier. And so we can actually drill down, and we open one of these sort of lossy graphs, and we'll see this. Now, when we were building this, this was the part that was really exciting. So when we generated this graph initially, it was really cool. This is essentially a plot of all 36 flows on a given provider combination along with loss. As you can see, there are three distinct strata to these flows. And this is essentially the confirmation we were looking for when we built this. We're seeing ECMP in action. I'll remind you that these flows are between the same source IP at the same port or at the same data center to the same destination IP across all the same carrier paths. So these are equal cost paths across the internet that aren't actually equal cost. Now, we can't say that we've enumerated all the ECMP paths between these sites. That's a traveling salesman problem or like an endpoint complete problem. And notably, layer 2 link aggregates, especially like really tightly defined ones, probably aren't showing up here as distinct strata. But we are seeing three distinct permutations of ECMP paths. So for case studies, we'll start with this one. This is what single path congestion looks like. This is pretty obvious congestion on a single carrier. In this case, you can see that there's a congested path on 2914 from Madrid back towards our origin in Dallas. So the column indicating the response path is showing the same congestion on every outbound path. At this point, we're actually using 3356 in both directions in these data centers, so there's actually no problem with our traffic. But NTT this week was having a really hard time with some cable cuts in the Atlantic, and they were getting a lot of congestion. So if we zoom in on one of those graphs, we can get a better look at what's going on. Now, we see that this is, again, the worst available path or provider combination, and it started to congest. And we're not seeing yet any tail dropping. There's none of those little blue or purple dots. But if we could zoom this out or kind of go a little further, if this was a live demo, you'd see that it actually eventually does start to tail drop. Basically, as the router buffers are sort of starting to fill up, the packets are starting to take longer to clear the buffer. And we can see the 50th percentile there in green, but the other percentiles are also going up along with it. The gray smoky bits below the green line are the 25th percentiles. And right there at like 1420, even they're seeing a ton of latency. So things are getting pretty bad on this link. And this is where it gets interesting. This is the same congestion, but now we're looking at individual flows. This is all 36 flows for this sort of provider combination. And in this case, we can see that 50% of the flows are congesting, while the other 50% of the flows aren't. This is, in effect, the result of a single router in an ECMP path going into a congestion situation. And it starts buffering packets. The packets that, for whatever reason, aren't traversing that ECMP path didn't feel any effect. If you guys were monitoring this path with ICMP, you'd have a 50-50 shot of actually picking this up. If you were sending a traffic across the link, then half of it would be perfectly fine. You wouldn't notice a problem. And the other half would actually be terrible. And it would get even worse as the router exhausted its buffer and started to tail drop. And again, reminder, same source IP, same destination IP, two completely different experiences depending on nothing more than the permutation of source and destination ports. We've chased these down with carriers a number of times, and issues like this one are frequently the result of a large customer sending a lot of traffic. That could be a database being sent across a VPN link. Notably, GRE tunnels that don't use UDP transport are really problematic because Again, GRE has no ports, so it pins itself to a single path. Oftentimes, it's the result of just the vagaries of geography. So an ISP router will pick up a link from a customer at one place, but it's equal cost pair, sort of laterally with it, won't get that link, so it congests when the other one doesn't. So this is the next case study, and this one gets a little more interesting. You can sort of ignore the upper row here. This is Los Angeles to Miami via 1299. We don't always have the same set of NSPs at every site. And so when we send traffic on a given provider, they'll sort of hot potato it immediately to the carrier that does have that route. And so in this case, 1299 is actually handing traffic over to 3356, who is having a problem in LA. And that's why we see the same loss pattern on both of them. And so we see, again, everything heading from Los Angeles to Miami is congesting. And in this case, by the little dots, you can see that we're actually picking up a lot of loss here. So let's focus on this one where the arrow is. There we go. We got behind on our flows. So here again is the flow, the 36 flow graph. And we can see the same thing as the last graph to a certain extent. Congestion on a single path, again, you can see that flat line across the bottom where the other path wasn't congesting. But instead here, the router started tail dropping packets. These little sort of smoky lines here is the percentage of packet loss we're seeing. So the lines across the bottom are saying that each of these flows in this blob of latency is actually tail dropping. And if you made 20 TCP connections across this, again, you'd see 10 that were fine and 10 that were just awful. It gets more interesting sort of when we look here and look at that middle column. You can see on this one that there's traffic loss across the board from Miami back towards Los Angeles. So here's the same path, but now we're showing the reverse path. So we can see there's still that big blob of congestion from Los Angeles to Miami there in the middle, and that's on the forward direction on 3356, as we just saw. But we're also seeing something else here. In the direction of Miami back towards LA, there's more or less consistent loss. Those little peaks right there across the bottom of this graph all traverse 3356. And they're generating loss, even the ones that were totally unaffected by congestion. You can see sort of before the blob of loss or the blob of congestion that even the flat paths looks like two potential ECMP paths, but they're all picking up congestion here. This is what it looks like when you have a layer 1 issue. The paths you see here aren't immutable. They sort of converge in some places and then diverge in others. But the fact that it's affecting all the paths equally means that it's pretty close to where you're measuring it from. In the end, we ended up sort of diagnosing this with an MTR, and we alerted Lumen that we were seeing loss, and eventually they ended up rebooting a line card in Miami, and the loss went away. So it was a layer 1 issue with an optic on their line card. So this brings up sort of an interesting point. We regularly detect packet loss somewhere on the order of 0.05%. That is 0.05% packet loss. That's pretty precise. Now, this normally wouldn't be something that would cause, that level of loss wouldn't be something that causes a user actual problems. You wouldn't even notice it with TCP. But on a 100 gig link, that means you're silently dropping 500 megabits a second of traffic. When we see sort of congestion across all paths and everything is breaking down, we often don't even escalate the problem. We sort of figure that NSPs already know what they're seeing. Our assumption is that they're sort of on top of it and they're going to take care of it. They understand when big congestion events occur. What does sort of universally cause us to open tickets with NSPs is when we see these long-term micro drops. It's our experience that these sorts of issues aren't well handled by NSP monitoring systems. I'm not sure if it's a disconnect between like monitoring on the photonics layer, or like maybe the drop rates are too small for anyone to care. But when we escalate these, we're almost always finding issues that the NSPs didn't know existed. And some problems that have persisted for days or weeks or even months. And it's important that Automattic, through having a very sort of geographically diverse network connected to a very diverse set of providers, we have a lot of visibility into things that you wouldn't normally see. These kinds of issues are just simply not discoverable by people who only see one side of the link. And so if you're monitoring only one side of the link, you can't find them. And even we have a really hard time diagnosing issues where we're the only one side of the link. And that is like issues to our users on ISPs and NSPs all around the world that we don't control. We can't see those issues like we can between our own two data centers. And those ones kind of hide on us. But this is a technique that NSPs can use yourselves. It doesn't need or require provider diversity in order to work. You can certainly pin this to multiple links on your routers and still get nearly this level of granularity on your error tracking that'll let you find these sorts of micro errors and problems with ECMP paths that might otherwise disappear. Cool. So now that you've seen a few examples of how we use this solution to find issues, the question then sort of becomes, what do you do with it? This case starts out more or less as we've already seen, and we're going to sort of temporally stick ourselves in the middle of that blob of loss you see there. This is a measurement from Atlanta to San Jose. You can pretty clearly see a period of loss located on AS 2914 in the direction of Atlanta towards San Jose. Notable, there's no rise in latency. So this doesn't look like congestion to us. We're seeing about a third of the flows, so about 12 flows, are dropping about 30% of their packets. So this looks like a really bad link. Now, the next step for us is to execute an MTR between the affected data centers to see if we can replicate the loss. NSPs are often not familiar with our sort of boutique monitoring solution, so we kind of have to try and prove it to them in a different way that's a little more conventional. Usually we do that with an MTR. Some carriers don't believe in MTRs, and we have to send them dozens and dozens of pings engraved on a stone tablet. We've done some pretty sneaky firewall rules on our hosts that lets us execute an MTR over the same set of ports and the same permutations of ports that we're currently running our monitoring on. And so that allows us to generate an MTR that perfectly mirrors the path that we detected problems. And if you saw the full dashboard, when we detect problems, we actually generate the MTR line right there on the dashboard to make it a little easier for us to troubleshoot. This is an MTR between our POP in Atlanta and our POP in Seattle, egressing on 2914. And if you look here, you can see it's pretty clear signal that the loss is happening between hops 4 and 5. And looking at the host names, it looks like it's somewhere between Dallas and San Jose. Well, yeah, we have an origin in Dallas. So I wonder if we're seeing the same thing there. Yep. We generally only throw an alert when loss affects the path we're currently using, and our network automation stack can't automatically resolve it. And you can ask me about that one later. But we see the exact same loss pattern. So now that we know what's happening, all we need to do is email the guys at 2914. So here we see, again, this is the per flow graph. And somewhere in the middle of that blob of loss, we got a hold of NTT, and we said basically like, hey, you guys have an erroring link between Dallas and San Jose. They actually didn't know about it. And they sort of trust us at this point. And so they found it immediately and pulled it out of the bundle. So I'd like to say a good show to NTT. This is illustrative, though, of one of the more interesting things that can happen. Earlier, I alluded that ECMP paths converge and diverge along every hop along the way. Flows don't stay together as they pass from hop to hop. And so what we see is a topology change occurring when NTT pulled the link. And we can see right around 6:15 UTC, they pull the erroring link out, and the packet loss immediately stops. So all those sort of jagged lines just go away. At this point, the link topology has changed, and the router probably in Dallas would have recomputed all the ECMP hashing functions and recomputed which links of things are sent down. And we see, kind of interestingly, one of the new permutations afforded by pulling the link actually afforded a lower latency path than existed before. So you can see that these two strata actually drop down to these two strata. And we only get a couple of flows on there, but that's a permutation that didn't exist prior to them pulling the link. So it actually got faster for some people on some flows. Cool. So this is the final case study. What the hell? It's kind of time for the audience participation portion of the talk. We've gotten pretty good at deducing what happens on links, but sometimes we're stumped. This is one of those times, so I'll set it up. This is a graph of Amsterdam to Johannesburg. Things are kind of rough getting into South America at the moment, and there's a lot of bottlenecked routes, a lot of single points of failure along the path. So here we're outbound on 2914 out of Amsterdam and returning on AS 37100 in South Africa. Immediately prior to this, 37100 suffered a fiber fault between Cape Town and Johannesburg. They managed to bypass it, but then things got really weird. Latency on the internet is surprisingly stable. If we sort of went through all the graphs that we see all day long, these sorts of jagged lines don't happen very often. Usually it's just a pretty boring flat line with a few little wiggles in it every time somebody does a topology change, but mostly it's just boring. But we can deduce a couple of things immediately here. We don't think there's a link quality issue, right? This doesn't look like an erroring optic. We're not dropping packets at layer 1. And we don't see too much in the way of congestion. The delta between the 50th percentiles in green and the 95th percentiles, which are like the really dark gray lines, it looks like a pretty normal 10 to 20 milliseconds. That's about average for the internet. In a congestion situation, we'd sort of expect that to rise by quite a bit. And so seeing something like this, we kind of want to know what's going on, so we investigate. Okay, yeah. The per flow graph doesn't really give you a whole lot of insight initially. It's an absolute mess. We can see some definite strata. Oh, thought there was an animation there. Indicating an ECMP, but things, oh, there it is. Things are really bouncing around. So when we look at the individual flows, again, I'll remind everyone, these are the same two hosts with the same two IP addresses in Amsterdam and Johannesburg at the same time, and the only differentiator between them is port number. And so we're looking at individual flows here. This one's not too unusual. Nice flat response time, a little blip in the middle. This is probably normal jitter. It's sort of a momentary bump in the road and everything goes back to normal. This one's a little more wonky, but still pretty much normal. This is what a graph looks like when a router is sort of getting close to congestion but hasn't got there. It's jittery, but the average sped here is only like 10 milliseconds. So, like not great, not terrible. This is where things get really weird. This starts out looking a lot like the previous graph, but it's actually even better initially because that's only about 1 millisecond to jitter. So not something we would consider congestion. But then it looks like a path shift. So it looks like the topology changed, and this jumped up, this flow, for whatever reason, jumped to a different path. We tend to see these kinds of instant jumps every time you to change the topology. So it looks like it shifts to a path that's at a really solid 167 milliseconds. And then about 30 seconds later, it shifts again down to 163 milliseconds. But again, really stable, these ones. This is even more odd. Really smooth graph initially, and then a whole bunch of topology changes. So we're about 7 to 8 milliseconds. So the baseline here is about 7 to 8 milliseconds higher than the previous flows. So this represents yet even more paths across their network. This one looks for the world like something flapping the flow back and forth between two different paths. It's sort of defined by 170 milliseconds and 178 milliseconds respectively. And then finally, yeah, this one. Nothing odd, nothing's moving. Hard locked at a very stable 164 milliseconds, and all is well. If we look through the whole list, we'd see all of these path shifts are happening at different times. There's not really any homogeneity to them. We have some theories as to what's going on here, but nothing I'd call concrete. I'm actually interested to see what you guys all have to say about it. We're not sure what will cause that kind of a flow graph. So feel free to blurt it out. Is it convergence? Is it something flapping? Maybe it's some kind of crazy link load balancing that we've never encountered before. And this is sort of a one-off case. We've never actually experienced anything like that before or since. And so that's it. On the lead up to this talk, we've actually open sourced the Pingo application. It's a standalone Go daemon, and we're providing the application as well as the Grafana dashboards used to diagnose things with it. And that's available from our GitHub. And if anyone wants to see how this looks live or has any more in-depth questions about the solution, then come and find us, and we'd be happy to answer anything you have to say. And hey, we'll always trade monitoring for transit links, you know, just in case. So does anyone have any questions?
Hello. I'm reading the question asked in our online chat.
Sure.
So first question, Matthew Petach, unaffiliated. Is 6 pairs of source and destination enough if intervening NSPs have 2 sets of 8-way internal ECMP links? You need at least 64 distinct source destination pairings to see an issue on a given link. Why not use more source destination pairs?
Yeah, so that's a good point, right? I think we alluded to the fact that we're trying to execute as many permutations as we can. We are subject, Matthew, to the sort of restrictions of host systems. As we start executing more and more flows, especially for us with 28 data centers, the number of flows we have to keep track of constantly increases very exponentially. We found that 6 by 6 or a 36 flow hash in practice yields effective enough data without yielding any more useful data as we increase the number of flows. Again, notably, the things like layer 2 link aggregates where you have an 8-way LACP link, usually those would be, you know, across the same set of backbones or the same set of fibers, and they just simply won't generate enough differential latency to show up in the graph. So we found 6 by 6 to be kind of a sweet spot. Certainly, we would love to monitor. We would love to have as much entropy as possible. We've tested it up to 64-way, so 8 by 8 flow hashing, and haven't found a material increase in sort of accuracy.
Thank you. Second question from Matthew. Why develop a new N-way UDP probe system instead of using many existing tools like UDPing published at GitHub?
Yeah, so we looked at some of the existing tools. Mostly it was about volume. A lot of the existing tools can't deal with tens of thousands of flows to generate enough data for us to use. And as well, perhaps a big portion of this is the data representation. So it's fine to generate the flows one-off or generate a series of flows, but then you have to actually figure out how to tear them apart and do some useful work with them. And so our solution generates the flows, but then also allows you to dump them into a time series database and pull that apart.
Thanks. Blake Willis there. Have you detected micro errors approaching Ethernet typical error bitrate? Perhaps a better way to phrase the question, what's the lowest bitrate, error bitrate that will kick off opening a carrier ticket?
So it probably goes back to the fact that in practice, uncorrected by something like forward error correction, there is no typical Ethernet bit rate drop. We will see, again, we're monitoring at the edge. So there are a host of technologies into the NSP networks like FEC that will sort of correct those errors silently for us. In practice, again, we see 0.05% reliably. We've turned it up, the speed of packets. We're running a packet across every flow every 500 milliseconds, so it's actually not that fast. When we turn it up, we can get the detection rate down to even finer bit errors. But again, it's one of those things where if it's less than like 0.05%, you know, it's almost needless to try and troubleshoot with a carrier. They're never going to find it.
Thank you.
Right. So if there are no other questions, thanks, guys.